everyone, my name is Maria Drout, and I'm an assistant professor at the University of Toronto. For the past few years, I've also been a visiting scientist at Carnegie, and I'm very excited about JWST. I, along with a global collaboration of about 70 scientists, are going to be using JWST to try and learn about the origin of the heaviest elements in the periodic table. So how are we going to be doing this? It's actually a bit of a whirlwind of a story that involves merging neutron stars, gravitational waves, and some of the most energetic explosions in the universe. But let me take one step back. Most of you have probably heard the famous quote from Carl Sagan: the calcium in our teeth, the iron in our blood, were made in the interiors of collapsing stars. We are made of star stuff. This is very poetic, but also incredibly nuanced. It turns out there are many different ways that stars can make elements. And there's actually been this huge debate for the last 50 years or so about where the heaviest elements in the periodic table come from. There were a couple of different options. On the one hand, you had supernova, the explosions of massive stars at the ends of their lives. On the other hand, you had neutron star mergers, which are the merger of two of the remnants that are left over after supernova in their own right. So pretty extreme situations here. Neither one of these were perfect. On the one hand, supernova are very common, but it wasn't clear that the physical conditions were exactly right to make these heavy elements. On the other hand, you have neutron star mergers, where we're pretty sure that the conditions were right, but these are very rare. In fact, until a few years ago, we had never had a confirmed case that we knew we had seen a neutron star merger happening. But this all changed in 2017, and it changed with the LIGO and Virgo gravitational wave experiments. They saw some jiggling of space-time, and in the past, most of what they had seen had been massive black holes merging in space. But in this case, it was different. They actually had detected two neutron stars merging. And we as astronomers got very excited about this, pointed all of our telescopes, including some at Las Campanas in this direction, and were able to capture the light from that same merger happening. This was incredibly exciting for a number of reasons, but one of them is that fading light that we see from the explosion is actually caused by the radioactive decay of elements made in the explosion. So by tracking how it fades over time, we can piece together what sorts of elements were made. So in 2017, we had the first evidence that heavy elements are actually made in neutron star mergers. Now you might be saying, wait a minute, wasn't that the point of what you were going to use JWST for? Why do you need it if you solved everything in 2017? Well, in 2017, we were only able to capture the light from this merging neutron star for about 3 weeks after the explosion. And that's enough to say they're heavy elements, but it turns out it's not enough to actually say how far up the periodic table did it actually go. But there are models that say if we can track the fading glow from a neutron star merger for about 3 months afterwards, then we can actually disentangle. How far up do you go? Do you actually make things like gold and uranium and other things like that? Things that are actually necessary to form life here on Earth, and we're still trying to figure out where they came from. So we need JWST because these neutron star mergers are very faint and very red. So we need a big telescope that can see infrared light, which is exactly what JWST is. So once it turns online, I'm going to be crossing my fingers, both for a successful launch, but also then once it's up there, LIGO and Virgo happen to just find another neutron star merger. We can point our telescopes at it to detect the light from it, and then point JWST to learn about where the heaviest elements come from. Thank you.